Hello, we're going to talk about intermolecular forces. And intermolecular forces are the attractive forces between molecules. And so there are several types. There's dipole-dipole. There's hydrogen bonding. There are London forces or dispersion forces, or sometimes London dispersion forces, whatever you want to call them. And there are ion dipole interactions. So let's first talk about dipole-dipole interactions. This is going to occur between polar molecules. In which we've got a partial separation of charge. We've got two atoms, X and Y, that because of their differences in electronegativities, for example, in this molecule, cause a dipole to be formed. We use some vector symbolism from physics to show like this. We have a partial positive atom X and a partial negative atom Y. And what can happen is these molecules can have attraction between the partial positive and the partial negative atoms. The greater the attractive force, the more tightly these molecules are held close to one another. In the gas phase, there are no attractive forces. In the liquid phase, we do have these attractive forces. They keep the molecules in this condensed state. But the molecules are free to move about. In the solid state, solid phase, molecules are held in place due to the very strong attractive forces that are present. And so the greater the partial charges, the more likely these molecules are going to be in a liquid phase, or even more so in the solid phase. And as you lower the temperature, the attractive forces have a greater chance of interacting. They increase. As you raise the temperature, the molecules have more thermal energy, and those attractive forces can be overcome. And so this little symbol that I have here is a lower case Greek delta. It means partial charge. It's not something like sodium and chloride where we have separate ions. We've got a covalent bond here, and there's an uneven separation of charge in the molecule, and that gives rise to the dipole interactions. And so, going back to looking at liquid phase versus solid phase versus gas phase, one of the ways that we measure the strength of the attractive forces is by the boiling point, or the melting point. And that the greater those values, the greater are the attractive forces. hydrogen bonding is a special case of dipole-dipole interactions. And this, we will encounter hydrogen bonding when we have a hydrogen directly covalently bonded to a nitrogen, oxygen, or fluorine, and it is strongly attracted to another nitrogen, oxygen, or fluorine. Why is this the case? If you remember about atomic radii, atomic size, nitrogen, oxygen, and fluorine, and you throw in hydrogen, are extremely small atoms, so they can snuggle up close to one another if you want to think about it. And nitrogen, oxygen, and fluorine are the three elements with the greatest electronegativity. And so it gives rise to this extra strong dipole-dipole interaction that we call hydrogen bonding. And so let's take something like water. Remember, water is a bent molecule. The oxygens are partial negative compared to the partial positive charges on the hydrogens. And so it can be extremely strong interaction between the hydrogen and the oxygens. The hydrogen on some other water molecule to an oxygen in another water molecule. This hydrogen bonding is sort of a misnomer. It's not bonding. It's an intermolecular force. So I wish they called it like hydrogen attraction or something like that, but they didn't. They called it hydrogen bonding, and so that's the name that we're going to have to live with. The next type of intermolecular force are the dispersion forces, or the London forces, or London dispersion forces. And this is when we have a fleeting, temporary, instantaneous dipole that's formed. And what it causes is an instantaneous dipole, or induces an instantaneous dipole in a neighboring molecule. And so let's just take something like fluorine, for example. It's nonpolar. Very nonpolar because they're completely even sharing of electrons averaged over time between the two fluorines because they have the same electronegativities. But at any fleeting instant, some of those electrons in that bond, if we want to look at it from this standpoint, might be a little bit closer to one fluorine than to the other, in which case it makes a partial negative charge versus a partial positive charge. And so now for that fleeting instant, we've got an induced, we have a temporary dipole. And that can cause, in a nearby fluorine, a temporary disruption of that electron cloud, where we have partial negative and partial positive charge once again. And so we've got these induced dipoles. And so with increasing size, the London dispersion forces increase. So the bigger the molecule, the greater the London dispersion forces. One measure of the size of a molecule is to use its molar mass, molecular mass. And the heavier the molecule, the greater the London forces. We'll look at some examples of this in another video. And the last example, or to look at ion dipole forces. And so the magnitude of ion dipole interactions depends on the charge and size of the ion, and on the polarity, the dipole moment, and size of the polar molecule. And so an example of this type of interaction, we've got some ions like sodium chloride that are in water, and we've got some water molecules that have their partial charges. And so you can see how the partial negative charge on the oxygen that can interact with the positive sodium ion, or the partial positive charge on the hydrogen interact with the chloride ion. And now you got a hint as to how these ionic compounds can dissolve in water, and how these ions can now become hydrated. They become surrounded by water molecules. And so this is an example of ion dipole forces.